Now, in terms of time, the time it takes for the electrons to start moving, generally we're talking in the order of microseconds, a millionth of a second. And in terms of how long it takes for, say, that electron to make it all the way over here, that on the order of seconds. This is DC because all the current is flowing in one direction, and technically current is flowing this way. The electrons are flowing the other way. Why? Because Ben Franklin had no idea about electrons. He assumed that electric current flow was positive, something positive that was flowing. The convention stuck, and then later on when they realized it was electrons flowing the other direction, they said, yeah, okay, we're sticking with what we've been doing for 100 years.
So so inside the wire, it's just like positive and negatives everywhere, or they're flowing from one side of the batteries to the other until each other equalize?
I mean, the positive and negatives, I mean, the wire is made of some material which has made of some atoms which have positive, got the positive nucleus and the negative charges around the outside. It's more complicated than that, but we'll assume around the outside. So, what was your question again?
So, inside the wire, is it positive and negative charged when it's
I mean, the positive charge inside the wire are the nucleus is the nuclei of the atoms.
Okay.
But the positive charges are not actually moving, not noticeably.
Okay.
Does that?
Yeah, that's good. Yeah, I get it.
So if it's the electrons that are moving, then, well, I got my negative side here, my positive side here. The electrons will come off and an electron will show up on this plate on the left side. Now when an electron shows up on this plate, it's going to drive an electron off the other plate, leaving behind a positive charge. Then the next electron shows up, driving another electron away, leaving another positive. And electrons are going to keep piling up on this plate, driving other electrons away, and so there is like this current flow with a gap here. Which, at first glance, might seem like it violates the current rule that I laid out earlier, that at any point current flowing in equals the current flowing out. And I've just asked you to accept that, and then later on in a month, we'll talk about what actually is happening in between in terms of current flow. So eventually, if you get a bunch of negative charges on this plate right here, again, it's more spread out than when they are in the battery. And over here, you get a bunch of positive charges. If the two plates are close enough to each other, then we can treat this like two infinitely large plates with a constant electric field between the two, like we were just talking about. So my positive plates are on the left plate, the positive is left, negative is right. The electric field flows from positive to negative. My electric potential decreases as difference in my electric potential is negative as I'm going in that direction, which is what we had figured out before when we established that this was negative 12 volts as I went this way. Now, if you think of voltage, more than just electric potential, but think of voltage as sort of the impetus to get electrons to move or get current to flow. The higher the voltage, the more push there is to get these charges going. Thus, the term EMF. Originally, it was thought that what voltage really was the electromotive force, because it was pushing these charges to move. Later figured out that it's not a force. Voltage is not a force. That's obviously related, but it's not a force. And so from what I have read, and not every textbook agrees with this, some textbooks say that EMF stands for electromotive force. I make the claim that EMF now stands for EMF. It used to stand for electromotive force, but it's not a force, but they kept EMF instead. The symbol for the EMF, the shorthand symbol, is an epsilon, which is one of the reasons why in some engineering textbooks, and I've only seen this in engineering textbooks, not the physics textbooks, that for voltage, sometimes they'll just use a capital E for voltage. Because you wouldn't want to have too many letters overlapping with others. Not energy, voltage. And so for those of you going into engineering, especially electrical engineering, I think you're more apt to see the E than the V. So anyway, EMF is basically the ideal voltage. So if I have a 12-volt battery, ideally it's 12 volts. Reality is that when I actually hook it to a circuit, there's some internal resistance. And so the actual voltage, the actual potential difference between the two leads in practice is not quite 12 volts because some is lost within the battery itself. So EMF, think of EMF as just that ideal, assuming that the battery is resistance free. Questions up to here? All right, why don't we take a small break here? I just realized we haven't had a break yet. The quiz was like a vacation though. We're done in a half hour, so let's not take too long. And we'll actually define capacitance and go through just some fun little exercises of how do you know what's what? As in, if I double the distance between them, how does the voltage change? Things like that. Anyway, let's take 5. I'm going to pause this and hope that I remember to turn it back on. All right, any questions now? I'm starting recording. All right, so as we look at this particular situation here, I've got the battery and I've got this capacitor. And I've drawn it as 2 parallel plates, but matter of fact, that is the symbol used in a circuit for a capacitor is basically 2 parallel plates, like that of equal length, as opposed to a battery where you got the short and long capacitor, you got 2 of equal length. Now, some capacitors are polarized, so it makes a difference in which way you put it in. I'm not dealing with that in this course, but you might also see something like this, which would also be a capacitor. It's just that there is a preferred positive and negative side to it. So it does, in this case, if you're setting up a circuit, it does matter how you put the capacitor in. What we're doing, it doesn't matter. Our capacitors go either way. So the purpose of a capacitor is to hold charge. Now, batteries hold charge, so capacitor, the difference between the capacitor and the battery is the battery, you're holding charge and you want to be able to come back to it whenever. And when you hook it up to something, the current comes out at some rate depending upon what you hook to it. Capacitor, you're storing charge. Typically for a capacitor, you want a very quick, sudden release of current. So I've got all this stuff right here and I've got this charge build up and suddenly I need a whole lot of current all at once. Now I can think of 2 examples of when you would need that, but I will open it up to you. When would you need a very quick, sudden amount of current flowing?
To start a vehicle.
Oh, I wasn't thinking of that one. I don't think that's stored in a capacitor though, is it?
You have like a battery charger and you push it on. Put it on.
Oh, okay, all right. Ooh, yes. Not the one I was thinking of either, but that works too.
In a general sense, would it be like in case of a power surge? You had too
Oh, a place to store it in case of a power surge? They actually deal with that slightly differently as opposed to storing it on plates because you still have to get rid of it somehow. You tend to have inductors in it to prevent any mass fluctuations.
A taser. A taser?
That's one of the ones I was thinking of. And then, I guess, potentially archaic at this point, hopefully not too archaic. The flash and the camera. Matter of fact, if you get one of the disposable cameras with a flash, you can turn it into a taser.
Yeah, I've seen that
Yeah.
Yeah.
If you ever decide to play around with that, please don't film yourself and put it on YouTube. Or if you do it to your little brother, definitely don't put it on YouTube.
Have you done it before?
No. I just seen these idiots on YouTube saying, hey, let's see if this works.
And it does.
Yeah, okay, so anyway, so we need to store a bunch of charge on here, and so we got these two things at play here. We have the amount of charge, and then we also have the voltage to get it on there, because if I reduce the voltage, not as much charge is gonna be on there. So there's a certain amount of charge per voltage that is going to define what we're calling capacitance. So it is defined, and I can put the third bar in there, as the charge over the voltage between the plates of the capacitor. Now, when over here, I kept pointing to this as the voltage because it's a simple circuit. Ultimately, it's the voltage between these two plates that matters. And it's not gonna be 12 volts if I got something else in the circuit, so ultimately, I could have a 12 volt battery here, but not all 12 volts going across here. So, if I have let's talk about units and then get into some numbers. So the units of capacitance, we'll stick with SI, would be the units of charge, SI units of charge, over the units, SI units of voltage, and the units of charge, or unit, singular.
Coulombs.
Please recognize that this C over here and this C right here do not mean the same thing. And unit of voltage. So the unit of capacitance is coulombs per volt, but that was too much for them to write. And so they called it the farad. It is one of the, I would say, few units that is named after someone, but is not actually the person's name. Anyone want to take a shot at what this actual name was? I thought you, what'd you say?
Fernando?
Oh, not Fernando. It would have been a nice change of pace since most of them were named after Germans and Britons. Faraday, named after Faraday. His name will pop up again later. I guess Volt was also named after Volta. So another one, not named, not the exact name. And Coulomb was named after Coulomb. All right, so I'm gonna make this a huge capacitor. Let's say 3 farad capacitor. What is the charge I can actually store on this? Well, I know what the potential difference of the crosshair is. It's 12 volts. Now, when I'm looking at over here, when I'm using this formula, I don't care about plus or minus. These are absolute values. So I have 3 farads is equal to charge divided by the potential difference between the two plates, which is 12 volts. And so therefore, the charge I'm storing on here,
36 coulombs.
yeah. And if you touch those two leads, you probably best case scenario is you lose your hand if you touch it with one hand. Yeah, there'd be all sorts of damage coming that close to that kind of charge. Because we do have a wide variety of backgrounds in here, we'll just show you what a capacitor looks like. These are capacitors. Bigger than what you typically see. If you open up the back of a TV, they're not this big. Those are microfarad capacitors. So millionth of a farad. To give you some idea of what a typical capacitance is.
So like in coulombs, there's micro, nano, and millicoulombs. Is there the same thing for farad or?
Farads, yes, absolutely. And so those typically, those are in microfarads. And if you look at it, you won't see the word micro sign, you'll see the letter U.
Okay.
And that's just because they had warned at the time, I guess I'll put that there. And we have some button capacitors also. Basically, it's a round disc with two leads coming off of it, and those are in the order of hundreds of nanofarads.
It's like a little slim. I think I've seen
Oh, yeah.
Yeah, that's what I was thinking.
So those are, most of these are 100 nanofarads.
So I'm guessing 1 farad is like enough to like search this whole building.
For the, what, the 3 farad or 1 farad?
Yeah, like 3 farad.
Yeah, that would be bad. But I like using, the 3's a better number to work with, so.
Yeah.
Realism or ease of math? All right, so I'm looking at these 2 plates, and, well, let's take it one step further here. I'm treating this like a surface charge density, or like an infinitely large plate, so it has a surface charge density. So the surface charge density is just charge divided by the area of the plate. So my charge is just whatever my surface charge density is times the area. My voltage, because my electric field is constant in between them, my voltage is just my electric field strength times the distance between the plates. Again, not worried about pluses and minuses because these, I only want to deal with the positive numbers. And I don't feel like drawing the absolute value signs, but they're there. Now, if I'm treating these as infinitely large plates, the electric field in between them, between the 2 plates, is sigma over epsilon. Now notice I didn't put epsilon sub 0, which I had done before. Epsilon sub 0 assumes that there is absolutely nothing in between the 2 plates. In essence, you've got a vacuum. If you're dealing with air in between it, the difference between this is permittivity of air, permittivity of nothing, are so close to each other that we assume they're close enough to the same thing. So in the lab, if you have nothing in between the 2 plates, we consider that free space. However, if I do have something in between, a dielectric, I have something that is an insulator, because if I have a conductor in between it, then I'm storing no charge, the charge is just going to go straight through it. So this accounts for the fact that if I have some insulator in between the 2 plates, which you will on Thursday. So this becomes sigma A over epsilon times D, which is just epsilon A over D. Now, knowing that the permittivity of free space is, I think it's been on the flash quiz, the 8.85 times 10 to the negative 12 in SI units. Knowing the actual value of the permittivity of object of various materials like paper is, that's a bunch of numbers. And so they decided to come up with a slightly different system. And so they have what is known as the dielectric constant. Not to be confused with the dielectric strength, that's something different. And it is the letter kappa. It's not a K, it's a kappa. And that is the permittivity of the material divided by the permittivity of free space. So I think for paper, for plain paper, copy paper, kappa, the dielectric constant for paper is around 1.5, somewhere in there. So from this, epsilon is just kappa times epsilon sub naught. And so my equation over here for a parallel plate capacitor is kappa epsilon sub naught A over D. The Q over delta V is true regardless of what capacitor you're dealing with. Kappa epsilon naught A over D is specifically for parallel plate capacitor. But alas, we don't have time to go into all the manipulation. We'll do some of it on your own on Thursday, and next Tuesday we'll get into more of the nice clean board examples. And I'll hand stuff back on Thursday. I have stuff here, but, yeah, I'll hand it back on Thursday. Mostly 110 stuff that I should have handed back in the previous class. But I wasn't recording myself saying that.